Hello, students. Today I'm going to talk to you about something big asset class emerging, big technologies emerging called from quantum finance. This is my book. Also already have a book. So I want to start with the quote from Richard Feynman. He said, "Nature is not classical, damn it. And if you want to make a simulation on nature, you would better make it quantum mechanical." This is Richard Feynman. Students, what you are looking at, it's not a chandelier, this one. It's a quantum computer here. So welcome to the quantum world. This is Joseph Bonaparte, Director for Externals, Director for Masters in FinTech. Why quantum finance and why now? Why I'm teaching you this? You can't believe it, my students. I'm doing this because we have in year 2000, we have a 23,400 stock asset security under traded every day. Now we have a 79,700 security traded every day. Now, I'm talking 25 years, we are 3 times we multiply. 3 times from now, from 80, we're talking about 240, 250 assets are traded every day. The current computer, classical computer, cannot manage this. So you need a better technology. So the book, I'm going to go through the book, skim it quickly, and then go through it, and then go to the lecture. It's about 308 pages, 5 sections, 2 chapters each section. And the structure of the book is quantum foundation, quantum algorithm, and then financial application. We care about financial application, but you need to know the quantum foundation, which I'm going to teach today. This one, quantum algorithm, I'm going to teach it today also, and financial application. I have a preface also, why you need this book, about the book, how to read it, acknowledgement, the chapter 1, section 1, section 2, 3, 4, 5, quantum foundation, and the other things here. And then quantum foundation, what is it? Quantum finance theory and design, what is it? Measuring, mapping, quantum, what is it? Quantum frontiers market. And then I created a quantum finance index also. It's here, I will teach you. There is a finance, something called 60-40 paradigm. That means most of the companies as of today, they give 60% equity, 40% bond. With the quantum computer will be different. So I'm going to start with foundation of a quantum computer. So what is that, a quantum? Quantum is a Latin word, means how much, how great. The history of quantum starts from 1900, which is the 20th century, early 20th century. And the last development is actually my index and my book, QFI. And the book's not published yet, so that's the reason the least development. I created something called Quantum Finance Index, and you will have an assignment to replicate the work for a different company. Students, in the 50s, this is what was the computer, the laptop that you have it like this small laptop now, or tablet. This is the way it was in the 50s. Now, this is the quantum in 2020s, quantum computer, big room here. We expect 100 years from now or 50 years from now, this is going to be something like a laptop. The quantum computer has a lot of pillars, a pulse tube, stale, mixing chamber, and the temperature should be in the Kelvin. Here are more information about what you expect, and all of these are generated by AI. But look at the temperature, 300 Kelvin, 2.7 Kelvin, and 0 Kelvin, 0 temperature, room temperature. So what is that Kelvin temperature? In Celsius, it's 0 temperature Kelvin. That means 273 minus Celsius. And Fahrenheit, negative 459 Fahrenheit. So near zero absolute temperature are needed to prevent decoherence, maintain a qubit stability, and superconductor. We need this shape of quantum processing near zero, which is about 273 minus 273 in Celsius, or minus 459 in Fahrenheit, to weaken the resistance and to work on the superconductivity to make it more productive. If you make it hot, it will not move, the stability will go, and also we need it to be isolated from the environment. Quantum foundation, the core concepts. The first concept, so I'm going to teach you the theory of it, is superposition. I have a coin here, tail and head. If you flip it, this coin, tail or head, tail or head, tail or head. So there are only either tail or head. But there's in quantum finance, quantum mechanics, there's a third position called superposition. If I toss this coin, when it was in the air and it spinning, this is called a superposition. So that means we didn't know 0 or 1. So it's between 0 and 1. We call this superposition. Simultaneously 0 and 1 or both. The second thing is entanglement, which is connection or correlation. The third, we need to teach about interference, measurement, and decoherence. Again, so we go to the coin here. So somebody flip a coin, toss a coin, so it's taking two phases. So we call this superposition. And there is a professor, scientific, well-known, Schrödinger cat, which is, he said, the cat is both dead and alive until we look. And this is what Erwin Schrödinger in 1935 to support why we need a quantum finance, a quantum computing. So he said the cat is both dead or alive until we look at this. So the superposition is beyond binary thinking. Classical bit, the computer you have, the tablets, the smartphone, all of that, we call it classical bit, and it's between 0 and 1. So 0 and 1, and the quantum bit it's a mix of both, alpha 0 and beta 1. Superposition, we call it psi. So the financial analogy, a portfolio that is multiple risk states simultaneously. That's really like a superposition the portfolio is. Enable parallel computing, richer probabilistic model. Einstein called, now we're done with the first one, the superposition entanglement, now that everything is correlated. Einstein called this spooky action at a distance. So Einstein said, so that's what he said. So what is that entanglement in a quantum correlation? Two or more qubits can become entangled or correlated. Quantum interference beyond the bell curve, classical versus quantum. So if you look at the classical versus the quantum, for example, if as of now we assume all of the distribution are normal Gaussian distribution, with the quantum, they will allow to disrupt this kind of distribution and become to be something like that. So for example, if you look at the return of a company, sometimes low, sometimes high, you think it's a normally distributed. But in fact, with the quantum computing, they see different distribution, and therefore your optimization will be different. Measurement collapse and probabilities. So now we're talking about superposition here. We didn't know 0 or 1 or dead cat or live cat. But at some point, you need to collapse. It collapses, the system collapse and become to be classical. So we have a quantum doing a lot of work, but eventually it will collapse and be classical. So the quantum computer will be collapsed to classical computer, 0 or 1. Eventually you're going to open the box and see the cat is live or dead, and hopefully live. So the probabilities become to be amplitude. Quantum logic versus classic logic, concept, state, correlation, logic, and uncertainty. Classical 0, 1, classical statistical, we call it entanglement. 0, 1, we call it superposition. So the states, 0, 1 in quantum, we call it 0, 1 and superposition. Correlation, we call it statistical. In quantum, we call it entangled. Logic gates and or not, Harmon, C naught and T. Uncertainty noise here is fundamental. We talked about this uncertainty, but we did not talk about the gates. So here are the gates that we have. In a classical gate, you have and, not, or, XOR, and this, out. So you have a 2 input, you get an out. You're going to get this not, like you put 1, become to be 0. And you have the 2 ones to get 1. If you have 1, 0, it could be 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1. Then you get, that would be an or. If you have 1 and 0, then become to be 1, 0 and 1. Also 1, 1 and 1. 1, 0 and 0 will be 0. That would be the or, XOR, and things like that. In the quantum, we have different things. We call it Hadmard. And here are the in optimization, the portfolio diversification, asset A, asset B, and we do this, the or and, it depends how you want to do it. In a quantum, we do hammered gate. And here are the comparison between the two. If you are interested in math, here are the mathematical matrices for identity 1, 0, 0, 1. And then for Pauli X, this is the one that you have for matrices. If you want to go more in math, I want to be less math. Superposition, quantum concept superposition, how it help you with finance analogy, portfolio diversification, wave function collapse, market order execution, entanglement like system risk, uncertainty principle is volatility and information interference, narrative fusion, and you have also more. So I put that also in different graphics, which is this and this are pretty much the same. Your homework. Your homework is 10 questions. So I want you to answer them. And here are the 10 questions. What is a qubit? Qubit is 0, 1 and superposition. It's a 0, 1 and superposition. That would be qubit, the classical 0, 1. Qubit 0, 1 and mix of both superposition. One superposition, which is 0 and 1 and both at the same time, both 0 and 1 at the same time. What is quantum entanglement? So you have it here, the questions. I want you to answer those. Now I'm going to go to algorithm. Quantum algorithm. After we learn about the superposition, entanglement, and interference, the second thing you need to know is how algorithm build on these properties. So what is that algorithm? It's a step-by-step quantum algorithm, step-by-step procedure execute on quantum computing using a qubit superposition entanglement designed to exploit quantum phenomena. So the first algorithm we have is the Deutsch-Jozsa Algorithm, which is 0, 1. Function can be 0 and 1 and executed with oracle and hammer gates. Second one is Shor algorithm, quantum factoring and cryptographics. And how he does it, he's put input, random guess, and the quantum frontier transform, classical post, and then you get output. Now, let me talk about this guy. This guy, he's a professor at MIT, professor of math. I'm trying to meet him in person, and hopefully one time I'll meet him. He's still alive. He's doing a great job. He's going to disrupt all the blockchain and the crypto. He has a methodology to break through your digital wallet. So you can guess what is your digital wallet. So when the quantum computing come in, crypto and blockchain they have to upgrade the software to match it. Otherwise, he can break anybody digital wallet. He can be the richest man in the world. Now he's a mathematician. He doesn't do the breaking, but people who have the capabilities, you can use his model to do that. So there is one chapter in the book about crypto and blockchain. The second algorithm is Grover algorithm. Alok Grover, he's Indian, from India originally, came to United States, and he did algorithm to speed up the process. In classical computer, you have to go, we do search, you go through all of this box, you need to see what is the key. He does it in a fraction of time. So you have to go through all of the boxes to know what is the key for you. With the Grover algorithm, it takes you didn't have to go all the boxes, square root of n. Suppose you have 100 data source and you didn't know which one you need. So here, square root of n, 100 square root of 100 is 10. So you save 90% of your time. For example, AI, you have a prompt in AI, ChatGPT or Gemini, and they start researching website. Instead to research 100 website, it will take you the top 10 website that you need to search. Grover's algorithm, again with Oracle query, goes through phase of target solution, diffusion, and then you get the solution. I'm going to finish with this classical, that's an input, that's a time. They call it O of n, Grover O of square root of n, and Shor is, this is exponential n to the power 1/3. Now, Yosef, quantum computing is not for now, it's for later and things like that. No, I mean, if you are a computer savvy, I can do this now, but if you're a computer savvy, you can start programming quantum and get some results. So Google has something called Google Colab, and here's the link. GitHub will give you Qiskit and other software to support your quantum computing. And IBM has also a quantum. So you can use with the cloud, you can start programming quantum. And then if you're doing a degree in computer science, I'm sure I highly recommend that you take a quantum class, quantum computer, and start working with that, because we know in 2028, quantum computing will be available now through cloud. And then we believe in the 2030th, you will have more quantum computing. I wouldn't be surprised in 2035 if Best Buy is still alive as a company. I hope it still be alive. I like Best Buy. So you will go there and they're going to ask you first question, you want a quantum computer or a classical computer? Probably you're going to get classical. You're going to say, but your children, your daughter, your son will say, oh, no, buy me a quantum. It's going to be more cool for them. But then eventually in 20, 30 years, no more classical computer will be more into. So there's another homework here. What is that quantum algorithm? What problem? Deutsch-Jozsa, Shor's algorithm, Grover's. And can we start quantum coding? The answer is yes. And here are the website you can answer the question. So you have a 2 homework, one about this 5 question, and the other one is the 10 questions. All of these are written. You have to put them in Canvas. Thank you so much. And this is the foundation. And so what we covered today, very fast, we did that. But at least now you know we covered the foundation and the algorithm. The next lectures will be finance application. Thank you so much and welcome to the quantum world.